Okay, hi everyone. Thank you so much for coming. My name is Beth. I'm the marketing coordinator here at Rangle. Part of my role is to work with our community manager to sort of really support and grow our communities online. So Rangle started from a meetup, and what we really want to do is support all the meetups that we have going on in our space. We're so happy to support Toronto AI from last year, and now when we have Dave working with us and Ryan working with us. And so I'm asking if you learned anything today to share on Twitter, something that you've learned with the hashtag #LearnWithWrangle. And if you do, we'll retweet it and we'll be so, so happy. But anyways, thank you so much for coming. Rangle is, if you don't know, Rangle is a digital transformation consultancy. So basically we work with clients and we start working on strategy all the way through implementation of digital experiences. So with that, I'm gonna introduce Ryan, who was trying to eat some pizza. But he's going to be talking about TensorFlow.
All right. So welcome everyone and thanks for coming. My name is Ryan Marchildon. I'm one of the machine learning developers here at Rangle. If you're interested in learning more about what we do generally or what kinds of machine learning projects we work on here, feel free to come chat with myself or Dave after the talk. So the focus of tonight is going to be on TensorFlow.js. So before we dive in, I just want to get a show of hands. How many people here are web developers? Okay, we've got a couple. Cool. How many people here have worked with any version of TensorFlow before? Okay, quite a fair number. And of those who've worked with TensorFlow, how many of you have deployed a machine learning model beyond a Jupyter notebook? So say on the cloud or in an application. Okay, a smaller number. Okay, cool. So looks like we have the perfect crowd for this talk tonight. If you're familiar with JavaScript but you're new to machine learning, TensorFlow.js is a great place to get started. And then on the other hand, if you're an expert already in Python-based TensorFlow, TensorFlow.js makes it much easier for you to share your creations with others. So I just want to give a brief overview of what the key takeaways are going to be tonight. So my hope is that this is what you'll get out of the talk. First of all, you're going to know what TensorFlow.js is. You're going to understand what differentiates it from other machine learning libraries out there and other versions of TensorFlow. And then we're going to talk about, I'm going to show you a number of examples that will get your creative juices flowing about what you can start building with TensorFlow.js. So you'll understand its unique advantages and figure out like where would it be useful for you in your projects. And that's going to be the first third of this talk. And the remaining 2/3 is going to be more of a tutorial style. I'm going to walk you through some code examples. If you've downloaded the repo already, you have an opportunity to basically code alongside me. And in those tutorials, I'm going to show you how you can really quickly get set up with TensorFlow.js. We're going to start coding. We're going to make a couple of simple machine learning models by the end. And then I'm going to show you how you can import a pre-trained model and do some basically in-browser extended learning. And so we're going to do a deep dive into the code of a fun game called Webcam Pac-Man. Okay, so let's get started. So what is TensorFlow? So just got to cover this in case there are a few that don't know. TensorFlow is a library for building, training, and running machine learning models. So this was developed by Google in 2011. It was initially their proprietary in-house library for all things machine learning and deep learning, and then they open sourced it in 2015. So TensorFlow accomplishes two things. Number one, training machine learning models is very computationally expensive. So when you execute your code, you want to be running close to the metal. You want it to be executing at a low level. And another thing is that you want to be able to take advantage of parallel computing on GPUs. So TensorFlow is built in C++, so it can execute your code at a low level, but you can program it in a higher level language like Python or R. So you don't need to touch that dirty C++ stuff. And the other thing is that TensorFlow simplifies a lot of the nuts and bolts and nitty-gritty involved in building a machine learning model. So what used to take, say, 1,000 lines of code, you can now do in 12. And there's been a lot of improvements to the library, to the libraries available that have even abstracted it up further, where now you can even think about building a machine learning model almost like with Lego blocks, like just defining layers and specifying parameters for those layers. So it's taken it from a task that, where you'd have to think like an academic, and now you can approach it a lot more programmatically like a developer. Okay, so a little bit about what it takes to deploy a machine learning model. So TensorFlow gives you the tools to build one and train one. That's great, but how do we get our model out into the wild? And if you're productizing something, I mean, it's only when you release it into the wild, basically, that you really start that learning process that allows you to sort of fine-tune its development. So in the past, this has been a fairly cumbersome process. So first and foremost, if you wanted to get set up with TensorFlow, you had to know Python or R, and to take advantage of GPUs, you had to have basically an NVIDIA GPU, and you needed to install a bunch of libraries, so that was cumbersome. But then to make your machine learning model available to, say, a web application or a mobile application, you'd have to deploy it on a server. So you might, for example, build a Flask server around it. You would have to think about things like how am I going to handle sort of volumes of requests coming in. So you might need to create a proxy server with Nginx and gUnicorn to do load balancing. You may want to deploy it on Amazon or Microsoft Azure or Google Cloud Platform. The reason being, you basically, as the sort of volume of requests come in, you might want to scale the compute resources available. So you might start using microservices where if you get a certain number, like maybe in the morning you're only getting, say, 1,000 requests a minute on your model, but maybe there's a peak period midday where you're getting 1 million requests per minute, and then you actually have to spin up additional GPUs to handle that. So you might need to Dockerize or containerize your model. You may even use Kubernetes, etc. But basically, there's a lot of additional hoops that you'd have to jump through. And then we haven't even gotten to the application yet. So JavaScript is basically the language of the web, and most often an application that runs in the browser or on a mobile phone will be developed in JavaScript. And then in order to talk to your machine learning model, that JavaScript, basically client-side application, would have to send API calls to your model. So it'd have to basically send prediction requests over the cloud. That might be, for example, if it's an image classification model, you might be sending images to that model, and then you'd have to wait for it to process that, and it would send a response which contains, say, a prediction of what's in that image. But long story short, there is a heck of a lot involved in this, and so it takes a while to just get to the point where your model can be client-facing. And then if you could imagine having to iterate over this process, so maybe once it's deployed, you learn something is not working quite the way you want it to, and you have to go back and retrain, and you have to go redeploy that model. So this is a lengthy process to iterate over, and it's hard to be agile with it. So at Google, that got people thinking, well, how can we really simplify this, make this more efficient, and also make it easier for web developers? Because basically the situation was kind of like this. So from the AI, so machine learning practitioner's point of view, okay, I built this thing, I'm trying to get people to use it. How do I do that? And then we have all these really spectacular, application designers and web developers that are like, this machine learning stuff, this AI stuff is really, really cool, but how do I actually pull that into my application? It's really hard to bridge the gap. So fortunately, in roughly 2017, there was an internal project called Deeplearn.js at Google, and that merged with their main TensorFlow team to create TensorFlow.js. So TensorFlow.js scraps basically that old way of doing things, and it gives you the ability to build, train, test, and deploy your model entirely within a web browser on the client side and using only a single language, which is JavaScript. So that really is a paradigm shift for getting these kinds of capabilities into front-end applications. So I'm going to spend a few minutes going through a couple of, basically flushing out some of the advantages that this brings to help you understand its significance. And then we're going to start going into some examples of what people have built with TensorFlow.js that will really serve to illustrate those strengths. Okay, so the first thing is apps are easy to share. Okay, you don't need to have anyone download files or install any libraries. You simply provide a URL link, and voila, the client or whomever you want to share your model with is working with it. So basically, all the dependencies are included as HTML script tags. You don't have to fight with virtual environments or package managers. And basically, this allows you to collaborate efficiently, prototype rapidly, and then deploy proofs of concepts painlessly. The second point is that the client provides the compute power. So you basically offload training and predictions to the user's hardware. And for you as a developer, that eliminates significant cost. You don't need to worry about keeping a potentially costly remote machine running on like AWS, for example. You don't need to worry about adjusting compute power based on changing request volumes or even service startup times. So it eliminates a lot of that back-end infrastructure overhead and lets you just focus on creating an amazing user experience with your machine learning model. Another crucial point is that data never leaves the client's device. So, I mean, as machine learning practitioners, we're all becoming increasingly cognizant of the importance of security and best practices, especially in the wake of like massive scandals like Cambridge Analytica. And with TensorFlow.js, users have the peace of mind that they're using AI without sending any personal data over a network or sharing it with third parties, because everything is done in their browser or on their device. So that makes it easier to build secure applications that would satisfy data security regulations. So for example, maybe you're building something in the healthcare space that's interfacing with wearable medical sensors. Or you might think of a use case where you're building a browser extension, maybe a Chrome plugin. You might be, think about one example would be narrating images, right? There's already tools that will narrate text for those that are visually impaired. You could imagine building a browser extension that will also narrate the images on the screen. And then that user has the peace of mind that, again, none of their browsing information is being sent to this tool on a cloud server or anything like that. It's all remaining inherently private. Next point is it gives you easier access to rich sensor data. So this is in the browser. The same application that runs in the browser can run on a mobile phone. And you have access to things like, within, say, a dozen lines of code, you can access things like the microphone, the webcam. On a phone, you also have GPS, accelerometers, etc. So it just makes it easier to get user inputs into your model, and that kind of feeds into the next point, which is because you've got easy access to user inputs, and because this is client side, it's easier to do real-time inferencing and build some really cool apps that basically respond dynamically to in real time to the user. So one example, here's a machine learning model that you can download already pre-trained called PoseNet. It's basically tracking say major joints within the body, like pivot points and also facial features. And this is all happening in real time. So you can think about basically building apps that might detect a gesture and associate an action with that, or might detect a user's emotion based on their facial expression, and then can sort of respond to that. So we'll do a deeper look into PoseNet later, and I just want to wrap up with a few additional points. So you don't have to reinvent the wheel when it comes to machine learning. You can tackle sophisticated tasks quickly by loading powerful pre-built models into the browser. And there's a growing number of models available. I have a link to a library of these models that I can share later. But basically, it's really, really easy to import these into your JavaScript code and start using them right away. And the other thing, too, is that it's also easy to basically fine-tune them to your application. So, for example, maybe you want to do an image recognition task on, I don't know, dog breeds, or, I don't know, Pokemon cards or something like that. You can download MobileNet, which was trained on about 1,000 different classes of images, from categorizing things like maybe a cat, a face, a car, a chair, a table. And there's huge value already in that machine learning model, because it's been trained on enormous data sets using compute resources probably beyond the reach of most individuals. And there's already a lot of learning that's been done about how to sort of interpret shapes and things like that within images. So then you can just tack on a couple of additional layers onto that network, and then just train those added layers to specialize in whatever task you want to sort of fine-tune it to. So that maybe that's, again, identifying dog breeds. We're going to see some examples later where we actually do some, say, extended training to program an app to respond to gestures. So that's one example of where you use a pre-trained model. And, okay, just wrapping up, actually, because I don't want to spend too much. I want to get to the code. But basically, anyone here have an AMD GPU and then, like, is ticked off at the fact that you can't use you can't use TensorFlow, like Python, with that, because you need to have this sort of CUDA library with NVIDIA. But that's not the case with TensorFlow.js. It's using WebGL. That lets your JavaScript basically sort of compile to a run on any GPU. So you can use an AMD GPU as well to train. Finally. Okay, there's like, I guess, a black market kind of thing for coder. Okay, all right, so it's getting better. But anyway, in the meantime, that's a stopgap. So this is more like the web developers care about this more so, like if you're doing back-end stuff with servers like Node.js, it's the same code base that you're using in your front-end applications. So the one downside is basically the performance is going to be limited by the client's hardware. So you're doing this on their machine. Maybe they've loaded up, like maybe your application works great on your phone, but then you've got somebody with a Samsung Galaxy S2 or something that tries running it. And of course, obviously, there's going to be a lot more latency there, and maybe it's not very performant. But there's ways to mitigate that, right? You can basically detect what hardware they have, and then you can basically choose to load a model that is smaller and trades off some of the accuracy for a faster runtime, basically. So there's ways to mitigate that. And things are getting better with hardware on phones. So all the major, say, chipset manufacturers, they're aware of the fact that, and they're planning for the fact that we're going to see more and more AI-based applications on mobile. So they've actually optimized some of the hardware to do on-device inferences. So that's getting, that problem is going to quickly go away. Very, very briefly, just a note on speed. If you compare TensorFlow in a browser versus TensorFlow, like sort of Python variant of TensorFlow, right now the JavaScript version is about a factor of 3 or 4 times slower. But the good news is if you hook TensorFlow.js up to Node, there's basically parity on the inference time. So I don't want to, we can talk about this kind of setup a little bit later, but I just want to move on now. Okay, examples. What can you actually do with TensorFlow.js? So I'm going to load one example here that's going to demonstrate, say, extended training in the browser on gestures. So this particular app, so you can control the output, either images, just really cutesy images, or sounds, and then you can associate that with a specific gesture. So for example, with this cat, what I want to train is images where, like, say, I've got my hand raised. So it's just basically taking snapshots from my webcam right now with my hand raised, and then maybe for the dog that's just, I don't know, undulating, let's get a different gesture. I'm trying to control the mouse with my left hand so I can put my right hand up. Oh gosh, just bear with me. So now this is my left hand kind of a little bit lower. Okay, so now if I put my right hand up, there we go. Left hand up, yeah. And then how about no hands? So let's just train on no hands. Oops. Oh, this button, yes. Okay, so did it capture that? Still thinks that. Okay, let's do a different gesture. I'll do, I don't know, thumbs up over here. Is it not? Oh. I don't know what happened there. Okay, something mucked up. But anyway, we can play around with this more later. But I must have done something. You know what?
This is an experiment that lets you explore how machine learning works.
Yeah. Okay. No, did my whole presentation disappear? Okay, sorry about that. Give me a quick second. It could be the angle as well, since I'm kind of like not fully, gestures may not fully be within the web browser. But in any case, okay, let's move on. So keyword spotting. So in this case, it's real-time, basically keyword detection in the browser. So if I say yes, no, stop, it's probably because of feedback. Stop, on, left, left. There we go. So you have an option. You have an option to personalize this. So basically, you can give it additional samples of you saying these keywords. And just a second. If anyone has, say, Google Assistant, you're probably familiar with like when you first set it up, it asks you to say hello Google 3 or 4 times. So there, what it's doing is it's got a pre-trained model, and it's just say fine-tuning some weights and some of the final layers to basically get an accuracy boost for your particular voice. So one thing that sort of to drive the point home that these fellows have done is they've made a voice-driven version of this game 2048. So if I say down, left, down, left, down, left. And so we could be here all day, right? But that just illustrates the point. This one's more artsy. You've probably seen arbitrary style transfer. And, oh, I don't want the blog post. Give me the demo. So basically what this application does is it takes the content of one image and it renders it in the style of another. So we're going to take this Chicago skyline and we're going to make it look like a sketch. So I'm going to load up a model here. And again, this model's in the browser. It's running its inference within the browser. Everything is entirely within JavaScript. Okay, so there's sort of a stylized version of that image. And of course, they have a faster version, which is sort of you've got that option if you're using hardware that's a bit outdated. Okay, and so you can do other things too, all right? So this gentleman, Brendan Suttle, has built an emotion extractor. And you can think about, say, an app, again, that picks up on the user's emotional state and might respond to that or change its behavior in some way. Here's a demo that we built internally at Rangle. This is taking that PoseNet that I showed earlier, which is tracking like facial position and points on the body. And it's just mapping sort of these Rangle glasses to my eyes. And then if I put my hands up, it recognizes that gesture and changes the style of the glasses. So anyway, I don't want to look like I'm flying here. why is, okay, there we go. So I don't know, kind of a cool look, maybe not. Very subjective. Okay, and so, besides really cool, sort of proofs of concept, what else can we build? Again, people are starting now to bring these, from the point of view of a user experience, bring machine learning into front-end development. So, thinking about applications that would learn from the user and improve, have basically being able to allow the user to define sort of audio shortcuts, like they can basically define their own set of keywords and train a model on that. And it's really up to, you guys and us a little bit to sort of push forward and develop new applications that take advantage of this in the browser. So if there's any folks from the academic crowd here, one other thing I want to touch on is that TensorFlow.js also gives you a really great way of just sharing your sort of results with other people or explaining new concepts. So this was actually the first TensorFlow.js demo, and it simply just explains what the concept of a neural network is. So you have basically two, say, classes of points you're trying to separate with a decision boundary, and you can control what features the neural network has, how many neurons, etc. And then you can actually train it in the browser. And the great thing about JavaScript and browser applications is it's fairly straightforward to make sort of reactive and animated components like this. Okay, so that's a little bit about what you can do with TensorFlow.js. So let's look at how do we get started. So for this, basically the tutorial is broken into 4 parts. The first is just fundamentals, basically how do we get set up with TensorFlow.js, a little bit about tensors, some of the nitty-gritty, some of the stuff that you need to know. Like if you already know TensorFlow, there's some things that are a little bit different in JavaScript, and then there's some other things we need to consider regarding memory management, because basically your memory restrictions are much tighter in the browser than they are if on a server, obviously. The next thing is we're going to look at building a really simple machine learning model, and I do that to illustrate, say, 5 key steps involved that repeat no matter how complex the model is. So basically, if you know how to implement these 5 steps, then you've kind of learned all the new stuff there is to know about the syntax, basically, of using TensorFlow.js. The third thing we're going to do, and I apologize if you've seen this done to death already, we're going to do handwritten digit recognition, but you're going to see how that gets done in TensorFlow.js with JavaScript. But the thing to note, though, is that for, again, those that use sort of the Python version of TensorFlow, if you're training a more sophisticated model, then you're probably logging metrics like accuracy and loss in a tool called TensorBoard. So TensorBoard does not exist for TF.js, but there's another tool called TF.js Visor that basically accomplishes a lot of the same functionality. In fact, I would argue it's better in some respects than TensorBoard. So I'll show you how to use that. And then the last thing we'll do, there's this fun game, Webcam Pac-Man. I'll show you that. Basically, you play Pac-Man with your head like this. I'll try not to get dizzy and upchuck, but I'll show that to you, and then we'll do deep dive into the code. And I'll basically show you exactly how they do the in-browser training from a pre-built model. Okay, so moving on. If you are interested in following along with the code, and you haven't already downloaded the repo, there's a link. It's also posted in Slack in the general channel. And if you're not on Slack, it's also online on the meetup page. And just a few other things. I hope that you have an IDE. I'm going to be using VS Code. And then for one of these demos, we're going to have to basically use a local web server. So just make sure if you've got Node, just install this particular version. It's easier to call from the command line. And then run your browser in incognito mode to avoid issues with syncing code. Okay, so if you're following along, you're going to see in the root directory, I've sort of organized these 4 topics into 4 different folders. And if you're new to JavaScript, so sort of HTML files, they define all the elements that exist in your web application or on your web page, basically, where these things are and how they're laid out in a nutshell. And then the JavaScript files provide all of kind of the logic that makes the magic happen behind the scenes. So the main.js file, many of these are empty templates, basically, that we're going to fill out together. And then if you want the completed code, that's in the reference file. Okay, so how do you get started with TensorFlow.js? No installations, you just add a script tag. So if we go to, let us go into the index.html file for our getting started folder. And all you have to do is reference a URL link in this HTML tag. And there you go. TensorFlow.js is available. So that's all you need to do. It's super simple. And so let's go through just some really, very, very quickly, some key operations. And I'm going to do a split screen here with a browser console. So again, if you, some of this might seem alien to you if, I don't want to do that, if you don't have any experience with web development. So those that do, just bear with me. So to get this page launched, you're just going to open up the containing folder and then double click on the index.html. So that's going to bring, I'm trying to do, so it won't snap to it. That's going to bring that page up. Right now it's just a blank page. And then what you're going to, okay, it's on another desktop, that's why. What you're going to do then, there we go. What you're going to do next is, if you're in Chrome, basically you want to go to, it should be not settings, whoops. Sorry. Just a bit tough to coordinate between two screens. Let me open that again. You want to go to your developer tools. So I'm just trying, I know the shortcut, but I'm just trying to find it in here. So more tools, and you go down to developer tools. So that brings up this side panel. And in this side panel, basically you can explore, it shows you what sources it's rendering the page from. But the tab you want to go to is console. So console basically shows you, if we log something, that's where it's going to show up. Okay, so let's get started. So one thing that is to note about TensorFlow is that whatever you feed into a machine learning model and whatever you get back from a machine learning model needs to be within an object called a tensor. And for all intents and purposes for us, you could just think of a tensor as a multi-dimensional array. So one-dimensional tensor is just a vector. So to do that, to define a tensor in this, you just basically you define a new variable here in JavaScript. You use const or let, and so TF calls the TensorFlow.js library, and then you just write tensor. So that's a method, and that the input to that method is simply a JavaScript array. So in this case, we're going to make a vector 1, 2, 3, and I promise I'm going to move on very quickly because for some I know this is painful, but it's important that we cover some of these key concepts so you're not confused later. So that's how you define a tensor. A scalar, which is just a single number. There's another method, scalar. For a two-dimensional tensor, and I'm just going to copy paste this code to speed this up. You basically have an array of arrays. You don't need to specify up front that this is a two-dimensional tensor, but you can. So this would be equivalent. Sorry, not that one. This would be equivalent, and it's just for readability. But just note if you see this elsewhere, it's not a requirement. Okay, so we've defined some tensors. How do we view the values? So normally in JavaScript, if you want to print something, in Python you just say print and then the argument. In JavaScript you go console.log typically and say we want to print the y tensor. So let's try this and see what happens. So I'm just going to save this file and refresh the web page. And here's what it returns. So it's not returning the values. It's basically showing you the entire object with all of its properties. So if you want just the values, there's a built-in method for tensor objects called print. So you just call that, and then if we save that and refresh the page, there we go, it's printed that tensor. Okay, the other thing you need to know is how to convert a tensor back into an array. So the machine learning model is going to give you back a tensor, but you can't go use this right away in your JavaScript code. You have to basically pull it out, and there's a few, say, idiosyncrasies with respect to how to do this. So let's just try it kind of the naive JavaScript way. Let's define an argument xArray or xr, and you would basically call this object array and then use the from method. And let's feed in our tensor x, and then let's just log it to console and see what happens. Missing semicolons left, right, and center. Okay, so if we do that, it gives us an output, but it's actually empty. So there's nothing in there. And why is that? Well, if you're used to Python, you're used to your code basically executing line by line, and the next line doesn't happen until the previous line has completed. But that's not the case in JavaScript. So in JavaScript, you've got to get used to this idea of synchronous code and asynchronous code. So if your web page was running its sort of main script, and every time it hit a block of code, it would just hang up and become unresponsive until that block of code was done executing, that would be really bad. So what JavaScript does instead is, if there's a task that is computationally more expensive, it'll just hand that off to like workers within the system and then continue running. So what can happen is, you may call this line and then expect this object to be populated with your tensor, but this is actually run, say, before that's been filled with the value. So one thing you have to do here is call a method called datasync. So just keep that in mind. And then when you do that, if you save that file, refresh here. Whoa, what happened there? Let's see. Oh, because I'm calling it on the wrong thing. So what you need to do is this. So yeah, you basically have to call that first on the tensor, and then assign it to your array. Okay, and now if we run this code, you'll actually get something back. So again, there's a couple little idiosyncrasies with JavaScript that you need to learn. Okay, simple math operations. I don't want to spend much time on this, so let's just take a look. There's cases where you might want to do some tensor math, and the reason might be maybe you're defining a custom loss function or a custom accuracy metric, and so you have to basically start calling math operations. So those are all available to you in TensorFlow.js. In fact, pretty much most of what you can do in, say, regular TensorFlow, you can now do in TensorFlow.js, so that's great. Lastly, memory management is a big concern when you're in the browser. So if you don't tidy up after yourselves, if you're not kind of removing unnecessary tensors, then what happens is you run out of browser memory very, very quickly and your application crashes. So the quick way to delete a tensor basically is you just call the dispose method. But there's a really nice wrapper called TF.js that will basically clean up after you for you. So let's just look at a sequence of operations here that would, say, construct like a polynomial of matrices. So we've got several intermediate tensors defined along the way, and then we print the result. So this is outputting this vector 8, 19, 44. But we can also look at how many tensors are currently within memory. So basically you just call TF memory and then access the property num tensors. So if we take a look at that, there's 8 tensors defined. If we want to basically automatically clean up after ourselves, then to do that, let's define a new variable called poly, just for polynomial, and then we're going to call this TF.tidy method. This is kind of tough actually because I'm looking at one screen and having to crank my head around. So to use this, basically there's a little bit of JavaScript syntax here. We're going to define what's called an arrow function. So basically it's just like saying, these are the arguments and this is the function. And then we're going to just take our code for this, all this math, and we're going to just put it within the curly brackets. So we can just cut and paste. And then I don't want to print that, I want to return the value. And then let's just print poly here. Okay. So now, if I run that, what? Should work. What did I do? I may have made a typo somewhere. So let me just quickly fix that. If you spot it, let me know. Oh, shoot. Yeah, I forgot to write sum. There we go. Something was missing. There we go. So we get that tensor, and now you see it's deleted the unnecessary ones. Before we had 8, now we've got 4. Okay, so I just wanted to point these things out. You're going to see this again and again in the code that we explore. So let's move on. So we're going to look at the linear regression task. Yep. Oh, I didn't return the value of sum. But generally speaking, yeah, if you're not used to JavaScript, yeah, JavaScript makes you, it's pretty old school. It makes you put that semicolon after every single line that you execute. Yeah, I may have missed one, and in some cases, JavaScript will kind of add it for you. So I think the source of the error there was that I wasn't returning the sum. Okay, so let's just look at now a linear regression problem. And we'll go through this again quickly. But the point basically is I want to walk you through some of the key steps involved in defining a neural net. And we'll go through this quickly. So first thing you need to do, of course, is convert your data into tensors. And then you define your model. So there's this awesome method you can call sequential, where it allows you basically to stack layers on like building blocks. So this is inherited from the Keras library, if you're familiar with that. And then there's a step involved to define an optimizer. So again, if you're new to machine learning, basically when you train a machine learning model, you first define a loss function or an error function. That basically, what that does is it's a measure of how good your machine learning model is doing. It basically would compare, say, the predicted output to what the output should be, and look at how different these are. And that would give you this error function, and what your machine learning model does as it trains is it basically walks along parameter space to explore this error function to try to minimize it. And so it uses basically optimization techniques such as stochastic gradient descent to do that. When you train it, you've got to define, what's the loss function and what optimization technique are you using. And then within a couple of lines, you can fit that model. So it's going to basically do 80 training passes over the data. And then once that's finished, you can call a prediction on it. So it's like really simple. In fact, if you committed this to memory, you would basically know all the new stuff you need to know that's unique to TensorFlow.js, like actually building a model. So let's do this together now. We're going to look at a linear regression task. And so just open up go to your root directory, and then you want to reveal this in a window, and then just double click on index.html. And if it doesn't load, like it did here, then open up an incognito window, and then just copy paste. Oh, I grabbed the wrong thing. I grabbed the old file. Pardon me. Oh, it's opened it on my other screen. Okay. All right, there we go. So I have some code already in here. What that code is doing is it's randomly generating some data points along a linear distribution. So basically, if you reload that, you're going to get different data. But I have some, basically, if you go into the index.html file, let's just make this a little bit smaller and this a little bit bigger. Within the index.html file, I've just defined some simple buttons. So if you're new, again, to web dev, you can just use this as a template, basically, for kind of mocking up whatever it is you want to build before you get into just designing it, making it look nice. But we're going to add a few functionalities here, so we're going to basically train a model on it, so that we're going to make this do something, and then we're going to plot a regression line. So very quickly, let's open up main.js, and let's code. So the data here is stored in an object, and it's sort of, you can think of this, you can access it like you can a Python dictionary. So we just have y and x. So if you can recall, basically, first thing we got to do is turn that into a tensor. So let's just be really quick about that, because you've seen that many times before. So there we go. Let's just put that array into this method. And next thing we're gonna do is define the model. So this is, again, this is super easy, using sort of this Keras library that TF.js has available. So you just define your model, and it's an instance of this object, sequential. Okay, and then once you have that, you just add layers to it. So you just define your network layer by layer. A couple things again about syntax. So within here, first we're going to call the name of the layer that we want. So in this case, it's a dense layer. So dense layer is just basically a layer of neurons. It's nothing special. And in this case, we're going to define a simple neural network that has a single neuron with has one weight and one bias. So basically, it's just going to take the input, multiply it by that weight, and add the bias. It's giving us the equation of a straight line. So to do that, we input the parameters using this JavaScript object. So to define an object in JavaScript, it's just curly braces. And then in there, we specify the parameters. So units 1, I just want one neuron. And then you also have to specify in the first layer what the input shape is. So basically the dimensionality and how many elements along each axis. So in this case, it's just a scalar, so we've got one dimension and just one element in that dimension. So boom, that's all there is to it for building that model. And the next thing we need to do is compile it. So we'll call model.compile. And within that, we need to define some parameters. So first one is loss, which specifies our loss function. In this case, we're going to use mean squared error. And then the second thing we want to do is define the optimizer. So in this case, I could use stochastic gradient descent and just type this in to get the default, but I actually want to specify what the learning rate is on that optimizer. So instead, I'm going to define a new variable up here, my optimizer, and then just tf.train SGG. That's basically referencing the name of this optimizer, stochastic gradient descent. Another popular one is Atom. And then I'm going to feed in the learning rate. So I'm going to find another constant, learning rate, and let's set that equal to 0.07. So I found that value to work well for this particular problem. So that's it. And next, train the model. So this is done basically in one line. Again, you call that model object, and now you want to use the fit method. And then all you do there is you pass in your data, so x data, y data, and then training parameters. So in this case, we're just going to have one parameter, which is epochs, and let's set that to 50. Now, there is a little bit of JavaScript nitty-gritty here. So this is an asynchronous function. So if I call this and then try to do something with it right away, it's not going to have returned the result yet. So one quick and easy way of defining a block of code that runs only after the previous line has run is basically by using this .then statement. And we won't get into the details. What this is doing is returning something called a promise. So when something returns a promise, and this is a method you can use. There's also things called callbacks, but you can learn about that offline. And so what this returns is a history object, basically, that would contain data about the accuracy metrics as a function of training epoch. So we're just going to add a little bit of code to this. So we're going to call a function I've defined called plot loss. That's going to plot the loss function using that history object. And then this is just a little bit of JavaScript to enable this infer regression line button. Okay, so that will become available only once the model has been fit. Okay, cool. So let us save that and refresh. Okay. So now, if I'm going to just open the console here. Oh. So as expected, there is something throwing an error, which is again probably because I'm just going back and forth like this. So can we spot what the error? Yes, okay. It's tf.layers, not layer. Sorry about that. Okay, so let's train a model. So it's training right now, and there we go. It's finished, it's plotted the loss function, so you can see that decreasing with passes over the data set. And next thing we want to do, so this button's enabled, but it's not doing anything yet. So let's get predictions now out of our trained model. So to do that, it's super simple once again. All we have to do is, again in one line, basically you call that model object and then you call the method predict. And what we want to do is perform predictions on our X data. And don't forget though, if you want to make sure that that tensor is available, you have to call data sync on it. Okay, and then to convert that tensor into an array, you just call array.from and then preds, sort of our data synced tensor. Okay. All right, so with that code added, I'm just going to put in a couple more lines here, which is just going to plot that line using some helper function I've defined, and then it's also going to enable another button, which is called get prediction. And before I reload this and retrain the browser, another thing we might want to do, of course, is get a prediction for specific user input. So let's just scroll down a little bit. And no, I don't want to save. And let's see if you can add, we've seen this example many times now. Let's see if I'll give you a couple seconds to code on your own to see if you can basically accomplish this task. So let's just wait maybe 20 seconds and see what you get. Okay, so probably what you did is, of course, you have to, actually should have pointed this out. So basically, this is the name of the variable you needed to use. Sorry for not pointing that out, but there are a couple minor differences here from what you might expect. So the first thing that you need to remember to do is actually what this gives you is an array, and it's not yet tensor. So you can't just put x input. You have to remember to convert that first to a tensor. Let's do that. There we go. And the other thing too is, in this case, it's a scalar, and this tensor by default is expecting something that's at least like a vector in dimensionality. So you also have to specify the input shape. So in this case, we're just specifying dimension one element. And of course, then again, you have to run data sync on this. And then for the predicted value, again, I should have pointed this out. So that's the name of the variable we want. So predicted value, you would call array.from, but you actually, that's going to give you back the array object, and what we really want is the first element of that object. So you just have to basically index it as such. Okay, so if I haven't made any typos now, if we rerun this, let's train the model again. We're going to infer the regression line. Boom, there we go. Not too shabby. And then let's just predict, say, at a value of 0.8, the y value should be. So it predicts 1.369, and on this dynamic plot here, let's go to 0.8. Yeah, that lines up with the orange prediction there. Cool. Okay, so that's how, in a nutshell, you build a machine learning model. Now, naturally, you're not going to be doing things, probably, hopefully, not as boring as linear regression. So let's look at something more interesting, which is image classification. So basically the task here, and it's a familiar one to many of you, is basically handwritten digit recognition. So you want to build a network that's able to take a 28 by 28 pixel input and map that to a specific number. So this is using an architecture called a convolutional neural network. Basically, a convolutional neural network it's like having a bunch of filters that get run across your image, and they look for, say, on a low level, the first set of filters might be looking for things like corners or edges, and then there's on the next level of filters, those would be running across so the activations of the first set of filters were, and trying to put these corners and edges together into shapes, so like a circle, a square, and as you go up to deeper within your network, basically, it starts learning kind of higher level features of the image. And then usually there is all these filters, the values within them get flattened, and it goes to, say, a dense layer of neurons that basically connect up to your, what's called a logits layer, that try to basically just map that particular, say, set of filter activations to one of these numbers. So this seems super complicated to newcomers, but again, TensorFlow.js, like Keras and Python TensorFlow, makes it super, super easy to build this network. So we're going to go do that together. We're going to fly through it real quick. But one thing that you might be wondering is, okay, well, like now we're getting into more sophisticated networks. What tools are available for me to very quickly look at, say, loss functions, to very quickly look at things like confusion matrices for evaluating the performance of a model, without having to go like every time manually define these elements within your web page. So it's a really cool tool, TensorFlow.js Visor, that does this for you. So in the next code sort of walkthrough, we're going to use that tool. So I've got, I won't get into the nitty-gritty of that code, like actually calling, like you can find it in the documentation, but you're going to see basically later on when you have more time, you can go through it in more detail and see how that code is working. Okay, one thing now for this particular example, we have to host this on a local server. The reason is because now we've got images. If you don't host it on a local server, you can run into a problem called cross-origin reference sharing. So we'll get into the details of what that is. Suffice to say right now, if you've installed the local web browser tool that I suggested, all you need to do is cd into that directory, and then gotta go up one level. And then you just type WS, or web server. And there we go. So it launches this on a local address. Let's just click that. And there we go. So let us put that in my incognito tab. All right. So right now, if we go into the code, first of all, to load this TF Visor tool, you just add an additional script tag. So this is getting kind of tough to read. So we've got the script tag that imports TensorFlow, and then there's another one for the Visor tool, and that's it. Right now this is available to you. So let's go into the JavaScript, and so right now, you go to the front of this, at the very top of the script here, you're going to see I've defined what's called an asynchronous function, and this runs basically as soon as the web page is loaded. And so basically, when you define an asynchronous function, if you get to a part of the code that is asynchronous and you want things to execute line by line, then you just call await. Okay. So right now it's just set up basically to pull in the handwritten digit data into this TF Visor tool. So the code that does that is at the bottom of this script. We can revisit it if there's more time. but basically, let's just get cracking and start building the model. So as before, we're going to use a sequential model. And it's super easy to build this. In fact, I'll just, rather than sort of agonizingly typing this all out, once again we call the add method. And now we're specifying a different layer type. This is a 2D convolutional layer. And then we just feed it a number of parameters. So input shape. So this is just, it's going to be like 28 by 28 pixels. And what image channels is, if you had a color image, this would be your color channels, like RGB. Kernel size, it refers to basically the dimensionality of the filters that we're moving across our image. Number of filters in this layer, 8. Strides just refers to the step size. And then a few other things. For each layer, you need to define an activation function. This is kind of what adds the nonlinearity to the neural network. And then we're also going to use a kernel initializer. So this just basically is a way of initializing the random, so like a random initialization of the weights that your network starts with before it begins training. And then usually we add another layer to downsample after a convolution. So again, I'll just, for the interest of time, I'll just copy paste this. Again, model.add. Now it's a max pooling 2D layer, and then pool size is basically kind of the area that it's sort of averaging over, and then strides is just again defining the step size. So this is going to be say a 2x downsampling. Okay, so we're going to add one more convolutional layer and one more downsampling layer. So there we go. Basically the same code repeated. Only difference is I've changed the number of filters. And then we're going to flatten that so that it can connect up to a dense layer of neurons. So just another layer flatten, you just call that. And again, of course, all these layers are being added sequentially to the model. And then finally, our output layer, we're not going to add an intermediate hidden layer because I just don't want this to take too long to train. But we just have like a final dense layer, which the nodes light up if it's a 0, a 1, a 2, etc. So that's a dense layer. Number of units is going to be equal to the number of classes. It's just 10 for 0 through 9. We're going to use a softmax activation function, and again, variance scaling to initialize those weights. Okay, so that's the model defined. Cool. Now let's go to model training. So again, going back to these 5 key steps, it's always the same. It's always the same, and that, in a way, that's really nice because again, you can get, you can then focus on, okay, what are the hyperparameters that work for getting a good result with this particular model. So in this case, we are defining. So we have to. Oh, there's one thing I didn't do. I didn't compile the model and define the optimizer. So speaking about 5 key steps. So same as before, we define a loss function. In this case, we're using something called categorical cross entropy, and we're going to define also a metric this time that we want the TF visor to track, which is accuracy. And then optimizer here, we're now using the Atom optimizer with its default parameters. Okay, model training. So what this code is doing is just setting up some metrics. There is another parameter you can pass in to your model.fit, which is callbacks. And this basically, if you use this TF visor tool, basically what this does is whatever metrics you pass in, it just starts tracking those. So it's if you've used TensorBoard and TensorFlow and Python, then you'll be familiar with this callback scheme. Okay, and then what we're doing here, we're just taking our training data and reshaping it, and also turning it into tensors. And you can see here the use of this TF tidy wrapper to kind of clean up after each of these sets of operations. Okay, so we're going to define the fit function right here, and we'll go a little bit slower in this one rather than copy paste. I will. Oh, you know what? Looking at the time, I am going to copy paste. So I'll just describe it here. So now, for those that are following along, you're probably just furiously typing away. But again, you have all of this in the reference file that's included. And I think the important thing is just kind of directing your attention and explaining each step. So again, here we've got the sort of x data, y data. So x, basically, these are, in this case, these are the images. And then y, these are the labels. These are basically saying, okay, image 1 is a number 5. Image 2 is a number 9, etc. So then batch size we've defined up here. So that's how many of the samples it's going to ingest at once. You may want to have a batch size that's smaller than the total data set size, because that introduces some randomness to your training, which can help you escape from local minima and converge to a better result. Number of epochs, shuffle, callbacks, so all of that is in the documentation. Okay, and then one more thing, evaluating the model. So instead of you having to kind of write your own functions for getting confusion matrices and plotting these, fortunately there's a number of built-in functions with TF.visor. You can get the per class accuracy, and you can also get the confusion matrix right away. And there's a couple of methods you can call to get basically TF.visor to render these in the browser. So all that work is pretty much done for us. Okay, so that's all there is to that. And now let's just uncomment this code, which is going to add the model training and evaluation when we run this application again. Let's just run it. Hopefully there's no errors. Okay, so there we go. It inputted the data, and now it's actually training the model, and it's updating. This is showing you the loss function and the accuracy, loss accuracy in real time as it's training. So that's cool. And then also as we plotted here. So okay, yeah, that's on the batch, and then this is on the epoch, because the batch might not be the full data set. So we'll just wait for that to finish training. And then it's going to right away run evaluation to assess the performance. So there, awesome. So right away, it's generated for us. This is the accuracy for each class, and also it produces a confusion matrix, which gives you an idea of like when the model's making mistakes, like where is it making them. You can see there's a couple instances where it's classifying a 2 as a 7, or rather a 7 as a 2, which is understandable. So you have all these tools at your fingertips, really. You don't have to reinvent the wheel. It's very easy to visualize training in the browser without, in this case, you don't even need to be an HTML expert to do that. Okay, so that gives you a feel for TensorFlow.js and how you can get started with it. Now I want to do something a little more fun. Let's look at Webcam Pac-Man. Okay, so let me just shut down that web server, cd back into my main directory, cd into the webcam folder, webcam transfer learning. Now, you may not be able to run this if you don't have some libraries installed. There's a tool called Yarn, which you need to basically install all the dependencies for this particular JavaScript project. So if you've got that, you can follow along, but if not, it's not super important right now. Then Yarn watch is going to let us basically build this and launch it on a local server. So it's just going to take a couple moments. There we go. Okay, cool. All right, playing Pac-Man with my head. I think I need to turn my webcam for this. So basically, once again, we're going to train various actions using webcam inputs. So, okay, it's kind of challenging for me to do this just because I'm looking at one screen and then having to run on another for the webcam. But let's see, this is me with my head tilted up, which is going to be the up command. And then me with my head tilted down. This is me for right. me for left. That's hard. I can't even see the screen. Okay, and then so this is the input data, and it's going to train. It's got a something called MobileNet. It's already loaded, which can do image classification. And now we've just fine-tuned it to associate different output nodes, basically, with these particular gestures. Okay, so let's play, and we'll see how well this goes. Okay, so I want to go up. I want to go right, down, right, or I mean left. Oh gosh. Oh. Can't even see where I'm going. Up. Oh, up. Right. Oh. So, let me know what your high score is, and we can have a leaderboard going on this, and also how long you can last before you get dizzy. But yeah, let's do a deep dive into the code and see how they actually make this happen. So loading model is super easy. In this case, they use MobileNet. Finally, we can full screen this. So index.js, that's the script you want to go into. Now, there's a lot of stuff here. We won't go through all of it. But basically, let us go to there. Okay. So first, near the top, there is a function called load truncated MobileNet. So to load a pre-trained model, all you do is you call TF load model, and if you're getting this from a URL, you just specify that. And if you're getting it from your machine, you just specify the directory to this model.json file. So whenever you export a JavaScript, a TF.js model, it does something called sharding. It breaks it into pieces, makes it easier to load it into the browser. And then it defines basically this model.json, which has some parameters and instructions for how to put those pieces together. So you reference that model.json file. And if you've been building your models in Python, there's a tool actually that, if you go on the TensorFlow.js website, there's a tool you can download and run from the command line that will actually take like a H5 file or a .pd file that you've like a frozen weights model, and will convert it into the JavaScript kind of equivalent. So you got a very quick and easy conversion tool, and then you just have to call this one command to get it into your application. So what they're doing here is they want to use the learning that is already embedded within this model, but they want to repurpose it. So once they've loaded that model, they're getting a particular layer from it. So this is a few layers back from the output. And the way this is going to work is basically as follows. And where is my presentation? This is like browser hell. Sorry. Okay, there we go. There it is. No, that's not it. Ah, here we go. So the way this works, so again, basically, they're going to bring in this pre-trained model, and they're going to add a couple layers on top of it. And now the problem is going to be defined a little bit differently. So the images that it's getting from me in the webcam, it's actually going to run those through that pre-trained model up until that layer that we picked out. And that output of this model is actually going to become the input to the classifier that we train. Okay? So it's not this data that's going into these layers, but it's this data already cranked through that model. And then it's just going to train this section to be able to associate, again, the webcam input with specific gestures. So let's go back to the code, and let's look at where it does that. So first thing, let's look at the definition for the model. So here it is. It's using TF sequential, again, and it's defining the layers within that. So the first layer, basically, is just flattening the output of the MobileNet layer that we've grabbed. So that's that layer that we've referenced, a truncated MobileNet, and it's just specifying the input shape to match the output shape of that. And then it's just adding a few additional units on top, basically a few additional dense layers on top of that. Actually just one, and then the second one maps to the class. In this case, there's 4, which is basically up, down, left, right. And that's it. That's all it takes to basically kind of train this, do some extended training. So same thing as before. They define an optimizer, they compile it with an optimizer and loss function. And then if we go down to the fit function, again, what they're doing here is, this, with it, basically they are first converting. So this should be, if we go down to controller data set, yeah, so what it does first, when it's making a prediction, is it's, again, running the image through the truncated mobile net, and then it's using that output and passing that into the model. Okay. So that's what's happening there. But as you can see before, it's basically the same syntax, the same kinds of functions we're defining, just put together a little bit differently. But that's the logic, in fact, behind this application, and that's how easy it was for them to, import a model and fine-tune it and do something really cool with it. So that brings us towards the end of the presentation. This time we have a bit of time for questions, and we also want to leave some time for us all to kind of socialize and mingle. But to basically wrap things up, so TensorFlow.js finally bridges the gap between machine learning development and web development or front-end deployment. Okay, so if you're a web developer, you can start to easily import AI capabilities into your applications. And as you saw, it's not much additional code. There's very little that you need to learn, and not a whole lot of work actually to get these things up and running. And also, you don't necessarily need to be an AI expert, because you can build on top of what others have already built. Okay, and with this conversion tool, you can also pull models that have been trained on, say, with Python. So that's awesome. And again, if you want to share what you've built with somebody, it's as easy as sending them the web address, basically. So I hope that was useful to you. I know with these presentations, it's always tough with a mixed crowd to kind of find the right balance, because you don't want to skip ahead necessarily of all the fundamentals. But I hope that was useful for you, and hopefully tonight, you're going to go home and start coding away and build something really amazing. So excited to see what you do, and hopefully that was useful to you. And feel free, of course, to send us some feedback. So thank you very much. Okay. All right. Awesome. Pizza time.
I just gotta grab the microphone.
Mm-hmm. You want the headset? Okay.
Okay, that's good. So this should be displaying in a moment here. I've got to mirror my screen. One second. So AI news. We've got some updates here. Okay, mirroring, arrangement, mirror displays. Nice, all right. Okay, all right, so first up in AI news, we've got the OpenAI 5 Arena just happened. Is anyone familiar with that here? Okay, some people have heard about this. So who here has heard of Dota? A fair number of people, okay. So for those of you who are not familiar with it, it's essentially a game that, I'm just gonna get my speaker notes on this. So it's an online game with approximately 500,000 players, like average daily players. They do a competition called the International every year. Currently the prize pool for that is right around $25 million. And so the OpenAI group has been working on this reinforcement learning based model over the past couple of years, and has been testing it out. And so they did really well recently. After the main competition, they tried out their model against one of the top teams, like top human teams, and it won both games in a match 2 out of 3. So they won the first 2, and that was that. And so then right after that, they announced the arena, which basically was several days, a few weeks back, where people could essentially sign up to play against the AI. And so it was a pre-registration where people could essentially go through and sign up for this thing. So the model itself had about 45,000 years of gameplay experience through reinforcement learning-based methods. So it's difficult for anybody to really match that. And there were 18,000 pre-registrations for the event. And basically it was that you just had to have a team of 5 people, and you would play against these 5 AIs that were cooperating as a team. So I've got some stats actually about some additional stats on the model itself. Let me just bring those up here. So they used 128,000 preemptible CPU cores on the Google Cloud platform with 256 P100 GPUs, also on GCP. And in terms of experience, it gained about 180 years of experience per day, and 900 years per day if you counted each hero in the game separately. So like 5 heroes on a team. Okay, so 45,000 years of gameplay in total, 18,000 pre-registrations. It played a total of 42,000 games against humans, and it took 459 games for the first human win to occur. All right, so here were the finals for that. It won 7,215 matches to 42, 99.4% win rate. This is for a game that goes for like a $25 million prize pool, so that's kind of cool. And total of 15,019 total players. There's the total number of games and total number of players there. So I had heard that they are maybe considering if it's going to be allowed to try to actually play this through the international event itself, like to go through the actual tournament versus just this open arena, to see how it would do in live competition. Okay, next bit of news is ICLR 2019 is coming up next week. That's in New Orleans, and there's a whole ton of cool papers there. A bunch of people from Toronto are headed down there. I'm going to be there. It's going to be fun. So this is a paper that I'm actually really interested in. This is by 2 people, possibly also 3. But I know Makarand and Sonia Fidler are both here from U of T. And this is one paper that I'm actually really interested in talking with them about. So it's visual reasoning by progressive module networks. And I'll just go through the abstract here really quick. So humans learn to solve tasks of increasing complexity by building on top of previously acquired knowledge. Typically, there exists a natural progression in the tasks that we learn. Most do not require completely independent solutions, but can be broken down into simpler subtasks. We propose to represent a solver for each task as a neural module that calls existing modules solvers for simpler tasks in a functional program-like manner. So basically neural nets, but functional programming. So lower modules are a black box to the calling module, and communicate only via a query and an output. Thus, a module for a new task learns to query existing modules and composes the outputs in order to produce its own output. Our model effectively combines previous skill sets, does not suffer from forgetting, and is fully differentiable. We test our model in learning a set of visual reasoning tasks and demonstrate improved performances in all tasks by learning progressively. By evaluating the reasoning process using human judges, we show that our model is more interpretable than an attention-based baseline. So this one's really cool because this is tackling one of the problems with getting us to AGI, which is scaling it out. So we can go really far by effectively scaling on a number of GPUs, but in terms of being able to learn a large variety of tasks and excel on a large variety of tasks, you need to be able to scale that out beyond the scales that we see now. Even though 128,000 CPUs and 256 GPUs, that's still relatively small scale to what would be needed for something that effectively has like global intelligence. Okay, so this one actually I found out about earlier today. on the way in. So Sarim is here, I think. Yeah, right here. Okay, so he's created this, he heard about the AI news as he was coming in. And so he's created a messenger bot for, do you want to describe it real quick? Like a 10-second?
It's basically a bot that will send you top 5 AI news every week. And you can also interact with it. So it's a messenger bot. So for example, you wake up in the morning, you're like, hey, I wonder what's trending in AI. And you can like hit a button and it will tell you, this is the top news. And it also shows you the top app too. I can go into like details of how I built it.
So do you want to mention this site?
Oh yeah, so the site, just go on Google and search for this AI news so last week. And then the first 2 links is basically, this. The first link would be the Facebook page, and the second link would be this web page where you can sign up.
Cool. All right. Thank you. Okay, and then so the other big news item here is also from OpenAI. They seem to be doing some really amazing things. So MuseNet, there's a link here if you want to check this out. It's openai.com/blog/MuseNet #try. And what they created is this transformer-based model. Recently, they came out with a model that was able to generate extensive tracks of coherent written text. They used a similar approach, also a transformer-based model, to create MuseNet for doing basically the same thing, but with music. And so I'd like to actually play one of those songs here. Can we cue the music? Okay, all right. Thanks everyone for coming out tonight. By the way, if anybody wants to say anything, we can do a quick open mic. Anybody out there while you have everyone's attention? Right here?